Before we move on to the next concept, let's look at a few more things here, like for example, the atomic mass. So if you remember, the atomic mass is basically the number that's right beneath the elemental symbol. So when you look at the periodic table, you see this number right below hydrogen. That's the atomic mass. And the unit of atomic mass is basically AMU. And AMU is short for atomic mass unit. And you can look at other elements in the periodic table like carbon, nitrogen, and oxygen, and you can clearly see the atomic masses of these elements. You also learned last time the difference between formula mass and molar mass. They're actually numerically equivalent, but the difference is their unit. So for formula mass, the unit is in atomic mass unit, AMU, and for molar mass, it's in grams per mole. So in the previous lecture, you were able to calculate the formula mass and the molar mass of carbon dioxide, water molecule, and some other compounds. And it's as simple as looking at the individual atomic masses of the elements in that chemical compound or chemical formula. And so, for example, for carbon dioxide, you have one carbon and two oxygen atoms. And so in order to determine the formula mass, all you have to do is add the atomic mass of carbon plus 2 times the atomic mass of oxygen. So that would be 12.01 plus 2 times 16, and you should get 44.01 AMU, which is the atomic mass unit, or the formula mass. And the molar mass would simply be the same number, except different unit. So it would be in grams per mole. Same thing for H2O. So hydrogen has an atomic mass of 1.01. So you would multiply that by 2 because you have 2 atoms of hydrogen, plus 16.00, which is the atomic mass of oxygen. So adding them together results in 18.02 AMU. So that's the formula mass, and then the molar mass would be 18.02 grams per mole. You also learn about the mole concept, and basically 1 mole is a unit. It's a unit of measurement, and we know that 1 mole is equivalent to this huge number, 6.02 times 10 to the 23rd power. And this number is known as the Avogadro's number. And the reason why we learn about the mole concept is because whenever you're whenever you're performing an experiment at the lab, we're dealing with atoms and molecules. And in a flask, in a reaction flask, you're dealing with billions and billions of atoms and molecules reacting together. And so we have to come up with a new unit that can accommodate such large numbers, and we call that the Avogadro's number. So you also learn how to convert from moles to number of molecules, or from mass to number of moles, and from moles to number of molecules. So for example, if you're converting from moles of carbon dioxide to number of molecules, you would need the conversion between moles and number of molecules, and that would be 1 mole is equivalent to Avogadro's number. And so when you're converting this, you want to write down what's given. So we're given 0.00325 mole of carbon dioxide. So you're going to write that down, and then you're going to use dimensional analysis, right? And so you're going to set it up. You're going to set up your dimensional analysis, and you want mole, the unit mole at the bottom, so that it'll cancel with this mole right here. So we want 1 mole down at the bottom, and then the equivalent of 1 mole in terms of number of molecules or number of atoms is the Avogadro's number. So 1 mole of carbon dioxide gives you Avogadro's number of carbon dioxide molecules. So we'll put that up top, and you can see how the number of moles will cancel each other out, and you're left with the unit that you want, which is the number of molecules. So you're going to plug this in to your calculator, multiply the numbers that are up top divided by all the numbers at the bottom. So in this case, 0.00325 times Avogadro's number divided by 1, and that gives you the number of carbon dioxide molecules. And then the last part, one of the other things that you learned is converting from mass of atoms or molecules all the way to number of molecules or number of atoms. And so you can do it step by step. You can convert from grams to number of moles first, and then from number of moles to number of atoms or number of molecules. And so let's say, for example, you're given 10 grams of glucose, and glucose is a type of sugar. And it has a chemical formula C6H12O6, so that means you have 6 carbons, 12 hydrogens, and 6 oxygens. So the first thing that you would want to do here is to convert the mass to number of moles. And you can see here that you would need the molar mass of this molecule before you can convert it to number of moles. And so you can set up your dimensional analysis here, or calculate the molar mass of glucose first, which is about 180.2 grams per mole. Okay, and then you're going to set up your dimensional analysis. You want to put grams at the bottom, right over here, and then number of moles up top, using the molar mass. So 180.2 grams down at the bottom per 1 mole. Okay, so that's the molar mass. And then you're going to cancel the grams here, and that basically converts it to number of moles. And then from number of moles, convert to number of atoms using Avogadro's number. So we're going to set up another train track here for dimensional analysis, and then we're going to put 1 mole at the bottom, which is equivalent to Avogadro's number up top. All right, so the moles cancel each other out, and now all you have to do is multiply all the numbers that are up top divided by all the numbers at the bottom. So 10 times 1 times Avogadro's number divided by 180.2, and that gives you the answer. All right, so let's do a little practice here. Again, you can pause this video if you like, if you want to try it out yourself, or you can just follow along. So the first question here is calculate the number of molecules for each compound. And the second question here is calculate the number of moles of oxygen for each compound. All right, so looking at the first one here, we have 2 moles of sulfuric, H2SO4, sulfuric acid. How would you calculate the number of molecules for this compound? So as you can see here, we have the number of moles, and so we can directly convert that to number of molecules using Avogadro's number. So we're going to set up our dimensional analysis here, and we're going to put 1 mole at the bottom, the denominator, and then Avogadro's number up top. And as you can see here, the moles will cancel each other out, and you get the unit that you want, which is number of molecules. So we're going to plug in 2 times Avogadro's number, and that gives us 1.2 times 10 to the 24th power. And then for the second part here, it says calculate the number of moles of oxygen for each compound. Number of moles of oxygen. So here it tells you that you have 2 moles of this compound. And if you have, if you're trying to determine the number of moles of oxygen, all you have to do is multiply the number of moles of the compound times however many oxygen atoms there are in that chemical formula. So in this case, we're simply multiplying 2 moles by the subscript, the number of oxygen atoms. And so in that case, 2 moles times 4 gives us 8 moles of oxygen per 1 mole of that compound. Okay, and you can do the same thing for the other elements in the chemical formula. So for example, if I ask you how many moles of hydrogen are there in 2 moles of H2SO4? Well, you can do the same thing. Just multiply 2 moles by the number of hydrogen atoms. So that would be 4 moles of hydrogen, 2 moles of sulfur, and a total of 8 moles of oxygen. All right, for the second one over here, we have 3 moles of water. So calculate the number of molecules for each compound. So if we have 3 moles of water, all you have to do is multiply that by Avogadro's number, and that gives you the total number of molecules, water molecules. So again, set up your dimensional analysis. The number of moles cancel each other out, and we get 1.81 times 10 to the 24th water molecules. All right, for the second question, calculate the number of moles of oxygen. Again, simply multiply 3 by the number of oxygen atoms, which is 1. 3 times 1 gives us 3 moles of oxygen atoms. And the third problem here, we have 5 moles of magnesium bromate, okay, MgBrO3, parentheses, and then outside you have the subscript 2. So if we're calculating the number of molecules, or in this case, it's actually formula units because of the fact that this is an ionic compound. Same thing with this one at the bottom. Okay, so we're looking at formula units and not number of molecules. This is an ionic compound. All right, so we're going to set up our dimensional analysis, and all you have to do is multiply 5 by Avogadro's number and gives you the total number of formula units. So that's a typo here. So this is supposed to be formula units of magnesium bromate. Now, to answer the second question, calculate the number of moles of oxygen, you have to take into account this number right outside the parentheses. So whatever that's inside of the parentheses, you have to multiply by 2. Okay, so if you have bromine, you multiply it by 2, you have 2 bromine atoms. If you have, for oxygen, you have a subscript 3 here, you would multiply that by 2, so you have 6 oxygen atoms. So now, to answer number 2, calculate the number of moles of oxygen, you would multiply 5 by 6. Okay, so 5 moles times 6 atoms of oxygen. And that would give us a total of 30 moles of oxygen. And the last question here, we have 0.5 mole of chromium 3 nitrate. Okay, again, this is an ionic compound. How do I know it's an ionic compound? Well, we have a metal plus a bunch of nonmetals. So this is an ionic compound. So to answer the number of molecules or number of formula units, we would multiply 0.5 by Avogadro's number. So in that case, we get 3.01 times 10 to the 23rd formula units of the compound. And for the number of moles of oxygen, we'll do the same thing here that we did from up top. So you would multiply the number of oxygen atoms that's inside the parentheses by the subscript outside. So in this case, it's 3 times 3, so you have a total of 9 oxygen atoms. And then you're going to multiply that by the number of moles of the compound. So that would be 0.5 mole times 9, and that gives us 4.5 moles of oxygen. All right, so here's another example, just to make sure that you understand the concept before moving on to the next concept. How many molecules are there in 85.26 grams of carbon tetrachloride, CCl4? Okay, how many molecules? So here you're given the mass, right? So you're given the mass, and it's asking for the number of molecules. So before you can move on to the number of molecules, first you got to convert the mass to number of moles, and then from number of moles to number of molecules. So the first step here, we're going to convert mass to number of moles. So we have 85.26 grams. Convert that to number of moles. And before we can do that, we actually need the molar mass of this compound. So 12.01 plus 4 times the atomic mass of chlorine. And that gives us 153.8 grams per mole. All right, so we're going to write down what's given. We're given 85.26 grams of the compound, and we're going to set up our dimensional analysis. All right, so grams goes at the bottom and the number of mole up top using the molar mass. So here you can see the grams canceling out, and then we can add another train track here to convert the number of moles to number of molecules. Okay, so this is a molecule. And we're going to add another train track here. So because this is the number of moles here, we're going to put 1 mole over here. so that they cancel each other out, and the unit that we want up top. So we have Avogadro's number of molecules. All right, so moles will cancel each other. And all you have to do now is multiply all the numbers up top divided by the numbers at the bottom. So 85.26 times 1 times Avogadro's number divided by 153.8. All right, and here's the second question here. How many formula units are there in 55.93 kilograms of sodium bicarbonate with the chemical formula NaHCO3? Again, this is an ionic compound because we have sodium, which is a metal, and a bunch of nonmetals. So we're basically going to use the same approach here, right? So we're going to convert from mass to number of moles, and then from number of moles to number of formula units. Now, notice that in this example, you're given mass in kilograms. And so before you can convert from mass to moles, you have to convert kilograms to grams first. And the reason why is because the molar mass is in grams per mole and not kilograms per mole. And so you want the units to match up before plugging it into the dimensional analysis. All right, so again, formula units is a term used for ionic compounds, whereas molecules is a term used for molecular compounds. So we're going to write down what's given, 55.93 kilograms of sodium bicarbonate. And the first thing that we're going to do here is convert to grams. And if you can do that in your head, that's perfect. If not, then you can use dimensional analysis and you can include it in the process. But in any case, all you have to do is multiply 55.93 by 1,000, and that converts it to grams, from kilograms to grams. So we're gonna go ahead and include it in the dimensional analysis here. So we're gonna put 1 kilogram at the bottom so that they cancel each other out, and we know that the equivalence here is 1 kilogram per 1,000 grams. Okay, so you have 1,000 grams for every kilogram. So kilograms cancel out, and then now you can include or add another train track here involving the molar mass of the compound, which is 84.01 grams per mole. So we're going to add another train track here. Now we're going to put grams at the bottom, okay, so that it'll cancel with this gram up top, per mole up top. All right, so grams would cancel out, and then now we're going to convert number of moles to number of formula units using Avogadro's number. All right, so train track here, and then these moles right here will cancel each other out, leaving us with the units that we want. So we're going to multiply all the numbers that are up top, so 55.93 times 1,000 times Avogadro's number divided by 84.01, and that gives us the answer.